All right, fifth grade, hello. It is Wednesday, the 25th of March, 2020, and this is our science time today. So if you could take out your books, we're looking at 6.9. I've been telling you, giving you some previews that we're going to start talking about rocketry and rockets the last few days. I've been telling you that was coming up. So we're on page 175. And we're looking at 6.9, 175. We're going to read 175 through 177 today. And you have a comp check to do with that, which you should have the templates for. I believe I gave those to you before we left. So let's look first at what we're looking for. So let's look at our comprehension check on page 177. And let's look at some things that they're going to highlight for us today. So I'm in section 1, which it says give the word that best fits each clue. Remember, I want those in complete sentences. I've given you examples on the template because remember, we learn things in context when we learn them in complete sentences, or at least that's one way to learn things in context. All right, so we're looking for a word that would describe the narrow opening at the tail end of the rocket. B, a small rocket used for signaling. We're going to figure out what that is called. C, a chemical compound rich in oxygen. D, the cargo that rides in the nose of a rocket. E, a guided military rocket. F, the place in a rocket where fuel is burned. Okay, we're going to look for words that describe those. And then section 2, it says identify each item as either a solid fuel rocket engine. We're going to learn about solid fuel rocket engines and liquid fuel rocket engines and or liquid fuel rocket engines. All right. So we're going to, there's A through G. All right. Used to propel fireworks into air. We're going to learn, is that a solid or a liquid fuel? B, can be burned off and restarted again in flight or on the ground. Is that a solid fuel liquid rocket? Solid fuel rocket engine or liquid fuel rocket engine. C, used in most military rockets and missiles. D, used in the space shuttle booster rockets. E, can be used only in large rockets. And F, used in all ancient rockets. And finally, G, allows the craft's speed and direction to be controlled in flight. So we're going to learn which type of rocket engine, a solid fuel rocket engine or a liquid fuel rocket engine. All right. And then section 3, read each statement and answer true or false. And you know how to do that. If it's false, you write false and then you make the statement true. If it's true, you write true and you just write the original statement. They ask us, A, is this true or false? Rocket engines do not need oxygen in order to burn their fuel. B, a gasoline engine could operate in outer space. C, the first rockets used gunpowder as the propellant. And D, kerosene is the best fuel for a liquid fuel rocket. All right, so let's start our reading, okay? Page 175, follow along with me. If you have ever, it says the power of rocket engines. If you have ever been to a fireworks show, we all love fireworks shows, you have seen rockets in action. Rockets come in many different sizes for many different purposes. Whether it be the small skyrockets that burst in the air on the 4th of July or the huge Saturn V rockets used to carry men to the moon. Now, both are rockets, a firework and moon rocket, so to speak, something that could take us to the moon. All right, rockets and oxygen. Steam, piston, and jet engines all use oxygen from the air to burn their fuels. We've been talking about that this week. In the steam engine, fuel is burned in the air outside the engine. In the gasoline and diesel engines, the fuel is mixed with air in the carburetor and then ignited in the cylinder. We talked about that. In the jet engine, fuel burns after it combines with the air rushing through the combustion chamber. We talked about that yesterday. All of these engines depend on air for their supply of oxygen. If you were to try placing them underwater, for instance, they could not operate. There's no oxygen under the water, in other words. Rocket engines also need oxygen in order to burn their fuel, but they do not get their oxygen from the air. Instead, they carry their own supply with them. Because they do not need air, they can run in places where air does not exist, underwater or in outer space. So that's pretty interesting. So we're going to learn more and more about that. Rockets made in China. Rockets have been used ever since the early 1200s, when the Chinese shot off the first fire arrows propelled by gunpowder. Other nations learned about the Chinese invention by having rockets fired at them in battle. Soon rockets spread all over the world. Men worked hard over the next few centuries to improve rockets by making them larger and giving them the ability to fly longer distances. During the 1800s, armies used rockets because they were much more frightening and dangerous than cannons. Do you remember the rocket's red glare Francis Scott Key wrote about in the Star-Spangled Banner? But these days, war rockets had but these early war rockets had one big drawback. They were very hard to aim and had to be fired in huge numbers to do any real damage, just hoping that something would hit the target that they intended. So here's an example of the Chinese fire arrows, where you have the rocket, you see in your book on the end there, and it would propel the arrow farther, faster. But they weren't always very accurate. Modern rocketry. So the first modern rockets were developed during the 1930s and 40s in Germany and the United States. These rockets were much larger and faster than their ancestors, than earlier rockets. They ran on liquid fuel, could be guided in flight, and carried a heavy payload. That's the cargo that rides in the nose of the rocket. Today, rockets have a great many uses. Without rockets, space exploration would be impossible. Rocket engines have lifted men to the moon and placed satellites into orbit. They also power the space shuttle. Guided military rockets are called missiles. Missiles can be fired from the ground, from airplanes, or from boats. Some missiles are small enough for a single soldier to carry. Let's turn the page. While others are large enough to deliver a payload of explosives to a target thousands of miles away. In peacetime, rockets as fireworks have entertained people for centuries. Century is how many years? Very good, 100 years. Specially designed cars, boats, and planes are sometimes powered by rocket engines. Flares are small, short-range rockets used for signaling. Okay, so all of that is pretty self-explanatory, and you can probably all relate to seeing something in a movie or reading about something in history about different types of rockets and how they were used. And we just went to the Science Center, and we saw some rockets there. And we saw the space shuttle. That was cool. So we saw those solid rocket boosters on the back, and that should be very much in the forefront of your mind, because we were just there a few weeks ago. Two types of rocket engines. So now we're going to learn about the solid fuel rocket engine and the liquid fuel rocket engine, and the difference between the two. Solid fuel rockets. In the process of manufacturing, meaning making solid fuel for rocket engines, chemical oxidants, oxygen-rich compounds, and chemical fuels are first mixed together as powders and then hardened into a solid substance called the propellant. The propellant is packed into the rocket's combustion chamber. When an ignition flame in the chamber touches the surface of the propellant, the fuel begins to burn by combining with the oxidants. Hot, expanding gases from the burning chemicals push rapidly out of the nozzle at the tail end of the rocket. The nozzle's narrow opening causes the gases to escape at the highest possible speed, and the escaping gases provide the thrust to propel the rocket forward. Okay? The rocket engine stops burning when all the propellant has been used up. All early rockets had solid fuel engines. The basic design of the engine has not changed since the first Chinese fire arrows were made. The only real difference between early and modern solid fuel engines is in the propellant. Early rockets burned gunpowder, but modern ones can burn a variety of different chemical fuels. So let's look at the picture of the solid fuel rocket on the bottom of page 76. Okay, so I'm looking at solid fuel rocket right here. All right, so we heard the term payload, and we see that that's right here at the front or the tip of the rocket, right? And the nozzle is down below. So these are some of the terms. The combustion chamber, obviously, the propellant is packed into the rocket's combustion chamber. So you see a picture of all of that. Here in the liquid fuel rocket, you can see the combustion chamber down here at the bottom. All right, so I want to read that and point out some terms of the solid fuel rocket engine that we've talked about. So it says the solid fuel is chemical oxidants, which are oxygen-rich compounds. And these fuels are all mixed together, packed together as powders. Then they're hardened into a solid substance called the propellant. Okay? The solid propellant. And so we see that here. They're all mixed together, those oxidant, rich, which are oxidants, which are oxygen. That's hard to say. Oxidants are oxygen-rich compounds, and they're all packed in here, and they're solid in here. Okay? Now, it says, I want to read that again. So the chemical oxidants, which are oxygen-rich compounds, and chemical fuels are mixed together as powders, then hardened into a solid substance called the propellant. The propellant is packed into the rocket's combustion chamber. So here is the solid propellants, and this is the combustion chamber. Okay? That's what it looks like it's saying to me. When an ignition flame in the chamber touches the surface of the propellant, what's going to happen? The fuel begins to burn by combining all those oxidants. And the hot expanding gases, meaning heat rises, it expands. The hot expanding gases from the burning chemicals push rapidly out of the nozzle. Here's the nozzle. So they push rapidly out of the nozzle, and that propels our rocket forward, upward and onward. Okay? And then the gases escape through the narrow opening, which causes the highest possible speed, and the escaping gases provide the thrust, like I said, to propel the rocket forward, onward and upward. And all of those, everything here will burn in that combustion chamber. Once it's all burned, then it will, it stops burning, and because the propellant has been all used up. And by that time, if it's like some kind of spacecraft, that's when you see it kind of just floating out, like we've seen it in movies and stuff. We can't see it with our eye here because it goes into a different sphere. There's different spheres, we know, in our atmosphere, so it goes into a higher sphere that we can't see. But that's when you see like the movies and it's out there floating. It doesn't need the propellant. The propellant gets it into the sphere where it can see the Earth from, thousands of miles away, or it can float around in the stars, literally, and view other planets and whatnot. So let's read a little bit more. I'm right here about the rest of solid fuel engines are best suited for all small, short-range rockets, such as fireworks and flares, and most military rockets. The largest solid fuel rockets ever built are the two booster rockets that help to push the space shuttle into orbit. So orbit is what I was talking about. Once it uses up all its propellant, it's floating in a different sphere, in a different orbit. But most of it says the solid fuel we'll see in fireworks. Those are things we can see from the Earth, and short-range rockets like flares, and most military rockets. But you also have things like the space shuttle. So that's a pretty wide variety. But most are like fireworks and flares, okay? The largest solid fuel rockets, like I said, ever built are the two booster rockets that help to push the space shuttle into orbit. It takes only 2 minutes to burn up the propellant in those 150-foot tall rockets. When empty, they are dropped from a height of about 40 miles into the ocean below. So the propellants, those boosters that got them there, they actually fall off and about 40 miles to the Earth. And so to the Earth, but part of the Earth that won't impact human life, which is the middle of the ocean. And we know that the largest ocean is the Pacific Ocean. That's right. So they can steer those in a way to make sure that they're going to fall in the ocean and not affect human life like in a city street or somewhere on solid ground, all right, where people can be hurt anyway. So solid fuel rockets have that combustion chamber where all those oxygen-rich compounds are put, chemicals, form of powder, packed together, ignited, thrust straight into the air. Not always straight. They kind of go straight and then they'll level off, obviously, to their destination. That payload, all of that is used up, that propellant, so to speak, and then, well, literally, I should say, and then they float around up there. Or if it's firework goes up, does its thing, comes back back down to Earth. You'll like at a fireworks show like at Disneyland or something, you'll see that the fireworks aren't falling and hitting you. They all blow up in the air, and then they're dispersed and diffused, and like you'll see the smoke, the aftermath of that. Okay, so that's what most solid fuel rockets are used for. Now, liquid fuel rockets. So think about that for a minute. If you have any questions about the solid fuel rockets, you can go back, look at the words in dark print. I'm doing my best to explain without being in front of you and being able to act things out as much as I normally would. So you're going to have to rely kind of more on what the book says, but I'm here to help with any of that, doing the best I can to make this come to life for you. All right, so now let's look at liquid fuel rockets. So we see the picture there. It says a liquid fuel rocket also carries both oxygen and fuel as propellants, but not in solid form. Instead, oxygen gas is condensed into a liquid by chilling it to a very cold negative 297 degrees Fahrenheit. Then it is stored in the oxygen tank in the rocket. Another tank in the rocket holds the fuel, such as kerosene or liquid hydrogen. Hydrogen is a gas at normal temperatures. Liquid hydrogen is the best fuel, but it must be cooled to a liquid at a temperature of negative 423 degrees Fahrenheit. Colder even than liquid oxygen in order for the engine to operate. Fuel from the fuel tank and oxygen from the oxygen tank must be mixed in the combustion chamber and ignited by a spark. When burned, the fuel combines with the oxygen and together they become rapidly expanding gases. The gases rush out of the nozzle at high speeds and propel the rocket forward. Okay, so liquid fuel rockets. So let's look at our picture here. We have our payload, the same in both rockets, then our oxygen tank, our fuel tank. Okay, remember, they're separated, our oxygen here, fuel, but then they're kept separate, but then they come together when they're getting ready to be propelled, I guess is the best way to put it, out of the nozzle, and that's when you see all the smoke and the fire coming out of the bottom of the rocket. You can see here, my book's smaller than yours, but you can see here the fuel tank. You see the yellow tubes, and then you see the oxygen tank, the blue tubes. They mix together, and then boom, you have your explosion, so to speak, of those expanding gases that propel the rocket into the air fast and furiously, right? All right, so liquid fuel engines can be used only in large rockets with enough space to house the necessary fuel tanks. Remember, we need both of these fuel tanks in there. So they're larger rockets. You're not going to see that in a firework, okay? So liquid fuel engines can be used only in large rockets with enough space to house the necessary fuel tanks, fuel pumps, tubing, and combustion chamber. Spacecraft use liquid fuel engines because they allow the astronauts to control the craft's speed and direction in flight. The rocket speed is changed by adjusting the amount of liquid that flows into the combustion chamber. The more fuel that burns, the faster the rocket goes. That's just logic. That's like when you learn how to drive, you're going to push on the accelerator, and the farther down you push, the faster the car will go. Okay, so it's the same kind of principle. I'm going to read that again. The rocket speed is changed by adjusting the amount of liquid that flows into the combustion chamber. The more fuel that burns, the faster the rocket goes. Direction is controlled by moving the engine's nozzle back and forth, or by firing small directional rockets in short bursts. Unlike solid fuel engines, liquid fuel engines can even be turned off and restarted either in flight or on the ground. I feel like that was one of the questions in our comp check coming up. This capability allows a rocket to coast through the vacuum of space without wasting fuel, and also to land and take off again from somewhere, such as the moon. So it can actually land and park on the moon, so to speak, and then they're able to restart it on the moon. If they weren't able to restart it on the moon, the astronauts, then they would be stuck there, right? So that's really important. So I want to go back to the paragraph above that where it says the more fuel that burns, the faster the rocket goes. Direction is controlled by moving the engine's nozzle back and forth or by firing small directional rockets in short bursts. So here we see the nozzle, so that can move back and forth and steer it. Maybe it's a little bit like a rudder on a boat, but I want you to think about, so let's say this is, I wish I had a real rocket for you here. Let's say this is my rocket. And let me use a pink one. You could probably see it better. And so here's my payload and here's my nozzle. And so nozzle will be the narrower opening. When they need to move it, okay, so they're in the atmosphere, they're floating around, so to speak. When they need to maybe change direction, go left or right or whatever, they'll ignite one of the rockets within it, and then they can, and it could go that way, and maybe they will ignite it again, and it can go that way, and then maybe, so they can change direction in short bursts. My is the rocket engine burst. So here we're going this way, and then we can change it this way, and we can change it this way. So that's really helpful. They can, if they're off by a degree and they need to get in through a certain window to come back down to Earth, and they need to change direction, they can ignite that engine and turn it in short bursts. So that's pretty cool to think about. So we see one of the major differences of solid and liquid fuel is the liquid fuel is for larger rockets and more of the rockets that we'll see that do space exploration and space travel. And so they both are incredible devices. And it's just something to think about, that all these really cool machines that we can use in space and things just that are fun, like fireworks. They come because of the ingenuity, the creativity of mankind. And we know that all creativity comes from who? Jesus, right? And that he's given us these brains and these hearts and desires to create and to grow and to learn and to expand. So those of you who love space, one of my best friends in the whole world wanted to be an astronaut when she was growing up. She didn't do that. She became a teacher. But she loved space as a kid and wanted to be an astronaut. So maybe some of you will create the next incredible rocket or a way to get to different planets in various ways, and know that all of those gifts that you have and interests and desires are from our Heavenly Father, are from Jesus, who has a plan and a calling for your life. And it might be to explore and go someplace that no one's ever been before. And so just know that it started with a simple rocketry, at least. We saw on page 175, started with a simple Chinese fire arrow. Is one of the basic first rockets designed. And now we have something as incredible as a space shuttle, which can take us to out there in the universe, in the Milky Way, the galaxy in which Earth resides in, and explore. So who knows what is in the future. One thing I want you to do is I want you to read about Nate Saint. This is an incredible story. And maybe sometime, maybe in the next couple days, I'm going to ask you about it. We'll talk about that, and I'll read it with you. But I want you to make sure that you read about this gentleman. He was an incredible young man who did incredible things and lost his life for the gospel doing it. And so I think you'll find that really, really interesting. One of the kind of missionary heroes. And so I'd like you to read that. All right. So do a good job on your comp check, and don't be afraid to shoot for the moon. All right. See you soon. Bye-bye.